Good afternoon or good morning, depending on where you are. My name is Professor Orata. We are continuing with our lectures in thermodynamics. Today we want to look at polytropic processes. Just to remind ourselves, before we come to the gist of the matter, remember we did discuss adiabatic reversible work. If you look at the earlier lectures, we have lectures on adiabatic reversible work. And we came up with the expression for work for that particular process, which said that that's for adiabatic reversible processes, adiabatic reversible work. We had seen that we came up with the expression PV gamma is equals to a constant. And of course, when you plotted the indicator diagram for that particular one, pressure versus volume, we had the isotherm and we had the adiabat, which was much steeper. This is P directly proportional to 1 over V gamma, that's the adiabat. And this was the isotherm, P proportional to 1 over V, that's the isotherm. Now, this was a general expression which we got for ideal systems. Now, expansion and compression processes, reversible ones, which conform to this equation of state, PV. Now remove the gamma. Remember, this for adiabatic reversible work, that gamma was the ratio of the heat capacities, the isobaric, isochoric heat capacities. Now, for polytropic processes, we are saying that in general, for expansion and compression processes we are carried out reversibly, they obey the equation of state PV is a constant. And so, in the case of a adiabatic reversible process, then that N is gamma. That is the ratio of the heat capacities. So, I repeat, that's for expansion, compression, reversible processes, which obey the equation of state. That equation of state there. Now, let us look at some important elements here. Let us look at some of the important elements here in terms of computation of work. We know that for PV work, we know that dW, for PV work, we know that dW is pressure times the change in volume. Is pressure times the change in volume. In other words, dW is equals to PdV. PdV. Now, when we have this equation of state representing these polytropic processes, we know that P1, V1 is equals to P2, V2, and that is equals to a constant. That is PVN. And so we have our PVN here, and we have P1, V1, N. So we want to develop the work expression. We want to develop the work expression using the PV expression for work. So if we have P1, V1, but N is PVN, then we see that P will be P1, V1, N over V raised to power N. So if we take this pressure expression from this characteristic equation which we have said is for polytropic processes and carry out integral calculus on it, then we will have, so if you apply integral calculus, then we have dW is equals to P1 V1 N over Vn dV. And so we proceed with that expression there. Let's proceed with it and break it down as much as we can. So if we integrate from some state, let's say we integrate from some state 1 to 2, 1 to 2, that is we're starting from some state point 1, moving to some state point 2. What's the state point? That's a point which is defined by some thermodynamic variables. So if we start from some state point 1, going to 2, state point 1, going to 2, then W. I repeat again, integral of dW is W, not delta W. Why? In our earlier lectures, we mentioned that we don't have delta W or delta Q because W and Q, that is work and heat, are path functions. They are not state functions. And we had mentioned that thermodynamic state functions also are exact differentials. They depend on the state of the system, the initial and final state of the system, not the path which you follow to achieve to promote your system from some state point to another state point. No, it depends only on the initial and final states. Those are what thermodynamic functions are, and the exact differentials, the exact differentials. Q and W are path functions. So when you integrate, you don't talk of delta W or delta Q. No, because W is a path function. That's why if you have W adiabatic, Q is 0, W non-adiabatic, Q is not 0. Because at that point, when you have a adiabatic path, Q is 0, non-adiabatic path, Q is not 0. Depends on the path which you follow. Now, let us solve for W. Let us solve for W. So then what do we have? So we are going to use the identity. We are going to use the identity which we have used significantly in our lectures. That's xn plus 1 by n plus 1 plus c. C is the integration constant because I've not put the limits there. So we leave it that if you put the limits, then you don't need to have the integration constant there. So let's rearrange our system. So W here is equals to P1 V1 V1n dV over Vn integral from 1 to 2. And remember now that when we have x raised to power y, that can be written as 1 over x to the power minus y. Similarly, 1 over x, the y, can be written as x to minus y. So I will use that identity here to take it to the numerator there, to take it up into my integral. Let us use that. So this becomes W is equals to integral from state 1 to 2, P1 V1 raised to power n V minus n dV. So when I do the integration of that particular one, then we see that W therefore is equals to the integral here. So we have it integrated. So we have P1 V1 n, then we have V, that is let's finish the integration there. I don't need the integral sign there now. Let me just work because we have already shown that there. So when we integrate it, just get V minus n plus 1 over minus n plus 1, state 2, 1. So we have just taken that up, V minus, then use the integration identity. If you integrate x power n, you get x n plus 1 divided by that. So it's just minus n plus 1 divided by that. So W is P1 V1, the n. What do we have here? So we have to V1, let's make it more comfortable, 1 minus n over 1 minus n, state 1 to state 2. It's more comfortable than talking about minus n plus 1. So just 1 minus n. Easier. So we have now W is equals to P1, V1, when you open up the brackets, V2, 1 minus n, minus P1, V1n, into V1, 1 minus n, over 1 minus n. So that's very straightforward arithmetic. So we just remember anytime we have integrated and we've gotten some expression like A, and that is 2, 1. So if we have, let's say, some value, we got a value natural log of V there, then you become natural log of V, 2 minus natural log of V1, that is natural log of V2 over V1. So that's how we open up that bracket you are seeing there. So we just call it them. But remember, we said that P2, V2, n is equal to P1, V1, n, and that's equals to PV, n. And so we can replace the P1, V1, n with P2, V2, n. So let's see what we get. Let's see what we get here. So we have, if we replace that, then W becomes P2, V2, n, V2, 1 minus n, over 1 minus n, minus P1, V1, n, V1, 1 minus n, over 1 minus n. Of course, can get a common denominator for this quantities here, so that W basically is P2, V2, V2, 1 minus n, minus P1, V1, n, V1, 1 minus n. And of course, 1 minus n. Let us simplify this expression here. Let us simplify this expression here. Let's simplify the expression. We use the laws of indices. It becomes very handy. And simplification there. Very handy for us. So let's use the identity which we are all familiar with. That is, if we have m raised to power x times m raised to power n, this quantity here, using this identity of indices, that will be mx plus n. So that's what I want to apply here now. Because remember, V2 raised to power n, V2 raised to power 1 minus n, that is V1 raised to power n, V1 raised to power 1 minus n, so I can add those indices. So that W now becomes P2, V2, n plus 1 minus n minus P1, V1, n plus 1 minus n over 1 minus n. And of course, those n's will cancel out so that we are left with W as P2, V2 minus P1, V1 over 1 minus n. That's expression for calculating work. And so you can plug this expression back. First law of thermodynamics, du is equal to dq minus dw. You can put in the work there for a reversible process. Then you know that for a reversible process, of course, du is 0, and so forth and so forth. Now, we talk of indicators. Now, when we draw the pressure volume profile for this polytropic processes, temperature, pressure versus volume. And remember, what is pressure versus volume? That's an indicator diagram. And the area under that curve is work. Because remember, pressure is force. over area. So volume, you know, is area times displacement. So pressure times force, pressure times volume is simply force over area times displacement. So the areas cancel out, you are left with force times displacement, which is work. So the area under those curves will definitely represent work. Now, when we go to the equation, that index of the polytropic equation, that index, we said PV, N is equals to a constant. This is N is sometimes referred to as expansion or compression index. Or index of the polytropic equation. So whatever you call it, it doesn't change what it is. Now, when this N is equals to 0, that N is equals to 0, then we'll have P, V raised to power 0, that is P. So pressure is constant. When N is equals to infinity, then we have P, V infinity. We have PV in infinity. So what will this be? This will be volume, constant volume. Because remember, if you handle the exponents here, there's 1, so if you divide by infinity, you have 1 divided by infinity, that's P to the 1 over 0, and P, that's 1 divided by infinity, which will be basically 0. Think about it, P 1 by infinity, that is P per 0, that is 1. And so you're left with the volume as constant there. You're left with the volume as constant there. So we have constant volume. Now, if N is equals to 1, then we'll have PV. N will simply be PV. That's an isothermal process. And if N is equals to gamma, where gamma is the ratio of the heat capacities, then PV N will be PV gamma. That's adiabatic. Now, what does that mean? We talked about adiabatic reversible processes. And remember, in the Rankine cycle, where with the axis was temperature versus entropy, where we had one of the steps, Rankine cycle, remember? So we have temperature, entropy, where we have temperature, entropy. This is the Cannon interface to the Rankine cycle. So you say 1, 2, 3, 4. This is isothermal. This is isentropic. That is isentropic. Isentropic process. What is constant entropy? Remember from Clausius inequality, yes is greater or equal to dq over t. So if it's isentropic, that is 0. Yes is equals to 0. Therefore 0 greater than dq over t. So dq is adiabatic. So this can be referred to as adiabatic or as isentropic. So if you construct the curves there, so we have where N is 1, for constant pressure where N is 0, constant pressure. And then we have where the volume is constant. We have said that there N is equals to infinity. And then, of course, we have the adiabat and the isotherm. This will be the isotherm. Along at the isotherm, N is equals to 1. This is the isentropic. Isentropic curve, and there we have said n is equals to gamma. So this is the kind of curve which you have. So here we have expansion. We have expansion, then we have compression. So now let us look at the significance of this slope. Because remember, we have pressure and we have volume. We have pressure and we have volume. And we have volume. What is the significance of the slope? This is the PV profile for this polytropic processes. PV profile. For the polytropic processes. Now, let us look at the implication of the slope. We have, let's look at the slope. We have PV n is equals to a constant. So the first thing is we just take the derivative because the slope is basically a derivative. So just use the identity for the product, that is the derivative of uv is u dv plus v du. Of course, f is the over x dx, and that will be dx dx. That's for the product. Now, if we apply that, take the derivative of p vn dv, that will be 0. Because the derivative of a constant, you know, is 0. So what do we have? So I use the product rule. Then we'll have vn dp over dv plus p dvn over dv is equals to 0. Let us retain this alphabet because we're going to talk about it. But you don't have to draw it again. Just have it at the back of our mind. Now, when we sort out this quantity, so we have vn dp over dv plus p dvn over dv. We use the identity. We know that d of xn with respect to dx will be n to xn minus 1. So we're using that differential calculus identity to sort out this particular one. So what we have, it will be n v into n minus 1. That will be n v into n minus 1 is equals to 0. Is equals to 0. Now, we can rearrange these particular quantities. So we have Vn dp. Let's use this portion of the board. Let's use this portion of the board. So we have Vn dp over dv is equals to minus n vn minus 1. Minus n vn minus 1. So we have dp by dv being equal to minus n vn minus 1 dividing both sides by vn, which turns out to be minus n vn minus 1 times v the minus n. So dp by dv is equals to minus n. Remember, we have said we add those indices or exponents. So we have v into n minus 1 minus n. So again, those cancel out. So we have minus n v the minus 1. Now, using the identity which we had just said earlier on, I just remind you so that you don't lose one another. That is, y to the minus 1 is 1 over y. I can apply that there if I use that identity. So dp over dv will be equal to minus n over v. Minus n over v. And so we are seeing that the slope is negative. The slope here is negative. It's giving us a negative quantity for the slope in this particular case. That is because that's P and that is V. And this expression here is not practical in terms of slopes, because that's why you see we are not able to use, we can only use this quadrant here. Let's call it quadrant 1. This is quadrant 2. But you cannot use this, let's call that quadrant 3. And this quadrant 4. Quadrant 2, quadrant 1. Now you notice that based on that kind of equation, what we are getting there is telling us that pressure is directly proportional to volume, and that violates Boyle's law. What he's saying is if you increase the pressure, you increase the volume. That's incorrect. In terms of empirical data, when you increase the pressure, the volume decreases, or vice versa. So we cannot use this quadrant, for example. We can use that one because it's reasonable, but we cannot use this quadrant here, where pressure, as you increase pressure, look, P1, volume is V1. We have P1, P2, volume V2. But what about in this portion here? If you increase pressure, volume increases. Increase pressure, volume. So we can't use quadrant 4 there. We can't use that particular quadrant because it would violate Boyle's law, which says that pressure is inversely proportional to volume. So for this polytropic process, polytropic processes, protons, we don't want to talk about protons, we want to talk about polytropic processes. So these are processes which obey the equation of state PV, n is equals to a constant. And you have seen the import of the value of n in terms of that, and we have looked at their indicator diagram, and see the indicator diagram is substantially different. But if you look for the isothermal process, even for reversible processes, for isothermal process, reversible isothermal process, PV expansion, we have V. Again, in that particular case, when you are talking of that, you will always have that isotherm there from V1 to V2. Of course, if it is irreversible, then it will be external pressure is constant. Now, when you are talking of adiabatic, then that slope is slightly deeper. So P is inversely proportional to V gamma. That is P, that is proportional 1 over V. So these equations is pretty accurate for polytropic process, reversible polytropic processes, and that's what we have looked at. So we will stop at this particular point and we'll continue with our thermodynamic lectures.